Hello, I'm Franco Piñan Basualdo, and today I will present you my work on thermocapillary manipulation at the air-water interface, work that has been done under the supervision of Pierre Lambert, Michael Gauthier, and Aude Polopion from the Free University of Brussels and the Femto Institute in Besançon. So let me first show you this quick introductory video. Well, our system consists of pointing an infrared laser to a water volume to heat the water, and this triggers a thermocapillary flow around the laser spot as shown here. And then by displacing the laser spot using a piezoelectric mirror, we can control objects floating on the interface. So let me start by first giving some more details on the flow itself, work that has been very recently published on physics of fluids. So what is a thermocapillary flow? The thermocapillary flow is the fluid motion along a fluid interface due to a temperature gradient. Whenever there is a temperature gradient, this creates a surface tension gradient along the fluid interface that creates a surface stress, and this surface stress drives the flow. And here to the right we can see the boundary condition, how to model this surface stress and how it is compensated by the viscous stress in the bulk. Normally these kind of flows, thermocapillary flows or Marangoni flows, are concentrated really close to the interface and don't have a big penetration in the fluid bulk. So the problem of using water as a fluid is that water is a polar fluid with very high surface tension. So it means that molecules like surfactants can very quickly and very easily absorb at the air-water interface, and when these molecules absorb at the interface, they reduce the surface tension. And if then you have a gradient on concentration of these molecules, surface concentration of these molecules, you will also have a Marangoni flow due to concentration gradients instead of temperature gradients, and this gets coupled with the temperature effect mentioned before through these two equations. So for the first equation is the transport equation, surface transport equation of surfactants. This means that the flow can displace these molecules and creates concentration gradients. And then the second equation is the surface stress balance. So if we think about it, it's a complex system because we have the flow that through transport affect both the temperature distribution and the surfactant distribution, and these two affect the surface tension that drives the flow. So it's a completely coupled system. We cannot decouple it very easily for high Reynolds number or Beckley numbers. Of course, if we neglect the convection, for example, we could decouple these two by we could decouple the surfactant and temperature transport from the flow, but this is not normally the case. So what we do to solve this system is basically run some numerical simulations, finite elements numerical simulations around the laser, where we simulate the laser heating and see how the flow develops around the laser. Here to the right, you can see in blue the fluid velocity that reached up to almost 35 millimeters per second, and in orange you can see the surface tension change due to temperature in solid line, in orange solid line, and due to surfactants in dash orange line. So we can see that at some point the surfactants gradient completely compensates the temperature gradient, and at that point that we denominate cat here, the flow is completely stopped. Just a quick mention here that the temperature increase is around 2 kelvins, so it's not very high. The effect of surfactant, therefore, is for low concentration of surfactants is to decrease the range of the effect and not so much the maximum velocity as shown here to the left. And these are also simulations, numerical simulations, where the initial surfactant concentration had an effect on the surface tension of reducing the surface tension up to 80 micronewton per meter. This is less than 0.1% change in surface tension. So these are really low concentrations of surfactants and can be due to uncontrolled pollution of the surface of the interface, and not due to an added surfactant. So we can then measure the range of this effect by placing a little bit of aluminum powder on the air-water interface and measuring how far the flakes move. And we see that the measurements match pretty well the simulation results. We can also measure the surface temperature with a thermal camera, and we can also see again that simulations and measurements match pretty well. And then we have a simplified model. We develop a simplified model where to find that the fluid velocity is proportional to the root square of the laser power, and that maximum temperature increase is proportional to the laser power to the 3/4 power exponent. Sorry. So let's jump to the robotics part. We can, as mentioned at the beginning, we can use this thermocapillary flow to control particles floating at the air-water interface. And here I'm going to show you some examples that were published recently also in Science Robotics. So let's see first, this is the top view of the system, and in red you can see the laser spot. This is the expected position of the laser spot because it's an infrared laser, we cannot see it in real time. There is a previous calibration step to correlate the mirror inputs to the laser spot position. But let's see what happens if we approach this laser spot to a particle. In this case, a 0.5 millimeter diameter steel sphere that floats on the interface because of surface tension, and we see that any misalignment is increased with time. This is because the system is unstable. The effect is repulsive, so it means that any misalignment of the laser spot with the particle will be amplified, and thus this suggests that we need a closed loop control. So how do we close the loop? We find the particle position through image analysis. As you see in this case, because of the backlight, the camera is saturated and it's really easy to track the particle position through image analysis. And if we keep the laser at a constant relative position of the sphere, we will see that it accelerates until reaching a steady velocity, as shown in the left plot. And on the right, we see that this steady velocity depends both on the laser power and on the laser particle distance, as expected. The problem is that the laser power cannot be varied very quickly. It takes a couple seconds to adjust the laser power. So it's much more efficient to use the laser particle distance as a control variable instead of the laser power. If we do that, we can close the loop and drive the particle to a target position, as shown here. So we see that the particle can be stabilized around the target. The problem is that, as you see, the taken path to the target is not the most efficient one, and this can be due to a bad calibration of the laser spot position, a bad calibration of the mirror, basically. So what is the advantage of this control technique with respect to magnetic fields, for example, is that the effect is local. It's localized around the laser spot. Thus we can control one particle, for example here, in this pathfinding example, when we see that particle 1 is moved to the target without affecting particle 2 and 3. This, I think, is the main advantage of this system. And again, we displace it to the target. Another advantage is that the laser has a very quick response time. The communication time is not that fast, but the response time is very fast. So it means that we can send several spots to the laser, to the mirror, save it into the internal mirror of the internal memory of the mirror, and then the mirror can switch between different spots in less than 2 milliseconds. So we can actually multiplex the mirror and use multiple virtual laser spots positions, that actually there is only one laser spot at a time, but you can switch between several spots so quickly that at the end it behaves as you had more than one laser spot. And by doing that, we can control, for example, 2 particles simultaneously to follow this loop, as shown here. Is still the same particles as before. Or we can, for example, control bigger particles. In this case, a 4-legged robot. We can see that we can displace the robot by placing the 2 laser spots around the 2 neighboring legs, or make it rotate, placing the laser spots around 2 opposite legs. And the rotation or displacement velocity, of course, depends on the laser power and on the laser's leg distance. By doing that, we can control these bigger objects around this loop, for example. In this case, well, we have 2 laser spots, then we have 4 degrees of freedom because we have the 2D positions of each one, but we limit it to 2 degrees of freedom, so only the distance to each corresponding leg of each laser spot, to limit the displacement only in one direction of the robot. So the robot always advances in the same direction. There is no perpendicular displacement in principle. We can control, for example, this also a 4-leg insect-like robot, in this case with only 1 laser spot, much higher laser power, and we can still control it. It's slightly smaller than the previous one, but we can see that with only 1 laser spot it's also possible to control it. But in this case we had to implement a multimodal control where the laser spot is jumping between different positions. It still works, but it wouldn't. I don't think it's as precise as the previous one. What could be the main application of this system? It could be the self-assembly assistance. So particles floating at the air-water interface or any fluid-fluid interface, alike particles attract each other. Because of the deformation of the interface, there is a lateral capillary force that make them attract each other. Also, this effect is also known as Cheerios effect. And we can use the laser to speed up the assembly, prevent defaults, or drive the assembly to a desired configuration that might not be the most preferred one. So, for example, here we see that without actuation, if we place these 2 C-shaped particles, they assemble in this configuration that in principle is the preferred one, the one that minimizes the surface energy. But with the laser, we can drive it to form a square, which is not the most stable configuration, and this is very robust. We can do it. It works all the time, unless the 2 particles were initially too close for the system to compensate. But we see that it's a very robust assembly. That's it for me. Thank you very much for your attention. I hope you have some questions to ask.